Hey everybody, thanks for watching here. There was a few more examples from Thursday's class that we didn't get through, and I just want to work through those. This is the first of two videos that I'm going to post today. Make sure that you watch the second one as well. That's got some new information in it. The first one that I wanted to work through, one that we skipped on Thursday, was this practice problem where we want to write the natural log of the cube root of x squared y over z to the fourth using logarithms of a single quantity. We want to break that down using the property of logarithms, so let's do that. Alright, just to clear up some space here, there's our original problem. So the first thing we'd notice is that we've got a fraction here, the logarithm of a fraction, and we know that we can break that up into two separate logarithms that are subtracted from one another. So the logarithm of the top, or the numerator, minus the natural log of the bottom. Now, these aren't single logarithms, these are logarithms, but they're not logarithms of single values. We've got x squared y and z to the fourth, so let's break those down more by bringing those exponents out to the front. If we do that, the expression becomes 1/3 natural log of x squared y minus 4 natural log of z. Now, 4 natural log of z, that is a logarithm of a single value, z. But we can break down x squared y a little bit more. So if we do that, we have to first of all recognize that we can break it up. The 1/3 coefficient is still going to apply to both logarithms, so make sure to use parentheses here. So we have 1/3 natural log of x squared plus natural log of y, and again that's addition since these two things were multiplied as the argument inside our first logarithm. The second term here doesn't change at all. Finally, we can bring that exponent of 2 down in front of the natural log of x, and at the same time we can distribute in that 1/3. So our final answer is 2/3 natural log of x plus 1/3 natural log of y minus 4 natural log of z, and we're done. Now let's look at one more example going the opposite direction as well. The problem in class that we skipped was 2 log base a of x plus 1/2 log base a of y minus 2 log base a of x minus y. So let's put those into a single logarithm. The first thing we have to address are these coefficients. We can't have them there when we try and put logarithms together. So we're just going to tuck them up and turn them back into exponents. So this becomes log base a of x squared. Our second term becomes log base a of y to the 1/2 power. And our third term becomes log base a of x minus y squared. Now these first two logarithms, since they're added, can become a single logarithm. And we'll take the product of x squared and y to the 1/2, which is of course the square root of y. So we have log base a of x squared root y minus log base a of x minus y squared. And since those two logarithms are being subtracted, we can turn those into a single logarithm by putting the x minus y squared in the denominator, and there we are. We've put these logarithms together and written them using a single logarithmic value. Okay, one more thing I want to work through in this short video, and that is the idea that we can use logarithms. This is an important property. We can use known logarithms to build other logarithmic values. I'm not going to work through all 6 of these, but I'll work through these first 3 example problems, and that should give you the spirit of how this works. So what we want to do is we want to calculate the log of 4 using log of 2, log of 3, and log of 5. Now if you have your notes, you might notice that this log of 3 I've changed. I realized I had a mistake. I had 0.44712. It's 0.47712. So there might be a discrepancy with your notes. So how to calculate the log of 4? Well, we can rewrite the log of 4, or we can build it using log of 2. Since 4 is 2 squared, that's the same as log of 2 squared. But then we can use the exponent property of logarithms to bring that exponent of 2 down to the front. And log of 4 must also then be equal to 2 times the log of 2. And that's useful because we know the log of 2 is 0.30103. So 2 times the log of 2 is 2 times 0.30103. So that means log of 4 must be 0.60206. So As it turns out, we were able to calculate log of 4 based on our knowledge of what log 2 was. You could check that with your calculator if you want, but we just want to see that we can build these logarithms. So let's do another one. Let's figure out what the log of 50 is. This is the common log, or log base 10 of 50. Well, we know what log of 2, log of 3, and log of 5 are. That's what we're given. So we'll build log of 50. We'll build it out of 2's and 5's. So 50 is equal to 2 times 5 squared. Now since that's a product, we can split that up into log of 2 plus log of 5 squared. We know the log of 2, so that's good. Now the exponent on log of 5 squared can go down in front and become a coefficient, so that's log 2 plus 2 times the log of 5. But we know log 2 and we also know log 5. It's 0.6989, so we can take log 2 plus 2 times log 5 and we get 1.6988, and that's within a tiny amount of rounding error exactly what log of 50 is. We built it out of smaller logarithms. For our last one, we want to calculate log of 1.5. Now, we can build that out of the 3 logarithmic values we know because 1.5 is 3 halves. So we can calculate log of 1.5 by finding log of 3 halves, but we know that log of 3 halves is log 3 minus log 2. And since we know log 3 and we know log 2, we can subtract those two values to get 1.7609. So log of 1.5 is 0.17609. You could verify that on your calculator if you want by taking the common log of 1.5, but again, within a little bit of rounding error, it works out nicely. Okay, that's it for this video. There is one more thing I'm going to cover in a second video here, so make sure to watch that one as well. That one's got a very important formula that you'll need to know in it.